In space, no one can hear you scream. It is one of the most famous lines ever written about the cosmos, and almost everyone believes it. Sound needs something to travel through. Space is a vacuum. Therefore, the universe is silent. It is a beautiful idea. It is also only half true. Because there are places out there where sound does exist. Real sound. Real waves of pressure moving through real material. There is a black hole in a distant cluster of galaxies that has been humming one continuous note for billions of years. So low that a single vibration takes 10 million years to complete. There are storms in the atmospheres of other planets that were recorded by microphones we sent there ourselves. There is a wind on Mars that a machine has actually heard. And there is one sound larger than all of them. Long before there were stars or galaxies or anything to listen with, the entire universe rang like a struck bell. That sound is still here. Astronomers have measured its echo, and it is written across the sky in a pattern 500 million light-years wide. Tonight, we are not going to look at the cosmos. We are going to listen to it. We will find out where sound can live, where it cannot, and how we learned to hear a universe that mostly refuses to speak. Turn the lights down. Close your eyes if you like. This one is meant for the ears. If you find calm in the quiet corners of the universe, consider subscribing to the channel. Let these slow, distant sounds carry you somewhere restful as we drift together through the dark. Welcome aboard, astronaut. Tonight we drift through the cosmos. We leave Earth gently, and the first thing that happens is the loss of sound. The rush of atmosphere against the hull thins, fades, and stops. Not muffled, not distant, simply gone. Out here, your own heartbeat is the loudest thing in existence. This is the silence everyone imagines when they think of space. And for most of the universe, it is completely accurate. But it is not the whole story, and the exceptions are extraordinary. Tonight we will learn what sound actually is, and why the vacuum refuses to carry it. We will visit a black hole singing the deepest note ever detected. We will listen to Earth's own magnetic field, which sings at dawn like a forest full of birds. We will hear what Voyager found when it crossed into interstellar space. We will discover that the early universe was dense enough to carry sound, and that we can still measure the wave it made. We will stand on Mars, where sound travels at 2 different speeds at once. And we will end with the record of our own voices, drifting outward forever. Some of what we hear tonight is genuine sound. Some of it is something else entirely, translated into something our ears can hold. The difference matters, and we will be careful about it. Settle in. Let your breathing slow. Let the silence become something you are listening to rather than something missing. Let us begin with what sound actually is. Sound is not a thing that travels. It is a pattern that travels through things. When something vibrates, it pushes on the material around it. Molecules crowd together, then spring apart, then crowd together again. That alternating squeeze and release moves outward as a wave of pressure. Each individual molecule barely goes anywhere. It jostles its neighbor and returns to roughly where it started. What moves across the room is the pattern of jostling. Your ear is a device for detecting that pattern. A thin membrane flexes as the pressure rises and falls. 3 small bones amplify the motion, and thousands of tiny hair cells in a fluid-filled spiral convert it into signals your brain interprets as a voice, or music, or wind. Every part of that process requires material. No molecules, no crowding. No crowding, no wave. No wave, no sound. The speed of sound depends on the material, too. In air at room temperature, it travels about 340 meters per second. In water, roughly 4 times faster, because water molecules are packed closer and pass the push along more efficiently. Through solid steel, faster still. The pattern is simple, and it holds everywhere in the universe. The denser and stiffer the material, the faster sound moves through it. And when the material becomes thin enough, the wave has nothing left to carry it. Now, let's go deeper into that emptiness. The air around you right now contains something like 25 billion molecules in every cubic centimeter. It feels like nothing. It is, acoustically speaking, an ocean. Interstellar space contains roughly 1 atom per cubic centimeter. That is the whole difference. Not a small reduction. A gap of about 19 zeros. With atoms that far apart, the mechanism of sound simply cannot operate. A molecule out there might travel for months or years before it happens to encounter another one. There is no crowd to push against. A pressure wave cannot form because there is nothing close enough to receive the pressure. This is why the vacuum is silent, and it is why the silence is absolute rather than merely quiet. It is not that sounds in space are too faint to hear. It is that the wave itself cannot exist. If a star exploded a few light years from you, releasing more energy in a moment than our sun will produce in its entire lifetime, you would see it. You would feel the radiation, but you would not hear anything at all. And yet the phrase every astronomer uses is that space is mostly empty. Mostly. That single word is where tonight's journey actually lives. Because in the places where space is not empty, where gas gathers and thickens, the rules of sound come quietly back into force. But that's not all, because the universe has such places, and one of them is singing. 250 million light-years from here lies the Perseus cluster. Hundreds of galaxies bound together by gravity, and the space between those galaxies is not empty at all. It is filled with an enormous cloud of gas heated to tens of millions of degrees, glowing in X-rays. That gas is still extraordinarily thin by everyday standards, but across distances measured in hundreds of thousands of light years, it is more than enough to carry a wave. At the center of the cluster sits a supermassive black hole. Material falling toward it is violently ejected in jets, and those jets punch into the surrounding gas, blowing enormous bubbles. Each bubble pushes on the gas around it. The gas is squeezed and springs back and squeezes again. That is sound. genuine pressure waves in a genuine medium. When the Chandra X-ray Observatory studied the cluster, astronomers found ripples spreading outward through the hot gas. Concentric pressure fronts, like the rings that spread when a stone lands in a pond. They measured the spacing between them and worked out the pitch. The note is B-flat, and it sits 57 octaves below the middle of a piano keyboard. To grasp that, consider the period. A single vibration of this note takes about 10 million years to complete. When one compression began its journey, our ancestors had not yet come down from the trees. It is the deepest note ever detected in the universe, and it has been playing continuously, without pause, for billions of years. And yet, there's more to this story, though here we must be careful because most of what you have heard called the sound of space is not sound at all. If you have ever listened to a recording of Jupiter, or the eerie whistling of Saturn, or the crackle of interstellar space, you were not hearing pressure waves. You were hearing a translation. Spacecraft do not carry microphones for this work. They carry antennas, and what those antennas detect are radio waves and plasma waves, oscillations of electric and magnetic fields, which need no medium and travel perfectly well through a vacuum. Here is the fortunate accident that makes it all possible. Many of these natural oscillations happen at frequencies between a few hundred and a few thousand cycles per second. Human hearing runs from roughly 20 to 20,000 cycles per second. They overlap. So a plasma wave rippling at 1,000 cycles per second can be fed directly into a speaker, and the speaker will vibrate the air at that same rate, and you will hear a tone. Nothing is invented, and nothing is exaggerated. The rhythm is real, the frequency is real, the structure is real. Only the medium has changed, from electromagnetic field to moving air. It is closer to a faithful transcription than to a special effect. And once you begin listening to the universe this way, it turns out to be an astonishingly noisy place. Now, let's go deeper and start with our own planet. Earth is wrapped in a magnetic field, and that field is alive with waves. We simply cannot perceive them directly. Every time lightning strikes anywhere in the world, it releases a burst of very low-frequency radio energy. Some of that energy escapes upward, travels along the curved magnetic field lines out into space, loops many thousands of kilometers above the planet, and comes back down in the opposite hemisphere. The journey changes it. Higher frequencies travel slightly faster than lower ones, so the burst stretches out along the way. What began as a sharp crack arrives as a long descending glide, a falling tone that slides downward over a second or two. Radio operators discovered these during the First World War, hearing them accidentally on field telephone lines and having no idea what they were. They named them whistlers, and the name has never been improved upon. There is something even stranger. In the radiation belts high above us, electrons trapped in the magnetic field generate rising tones, arriving in overlapping bursts. Played through a speaker, the effect is uncanny. It sounds precisely like birdsong at daybreak. Astronomers named it the chorus, and because it is often strongest in the hours around dawn, they call the strongest form the dawn chorus. Our planet has been singing this way for as long as it has had a magnetic field. Every sunrise you have ever seen was accompanied by it. We only learned to listen a century ago. But that's not all, because the nearest star is also full of sound. Real sound this time. The Sun is an enormous ball of dense plasma, and dense plasma carries pressure waves beautifully. Deep inside it, turbulent gas is constantly churning, and that churning generates sound continuously, in every direction, everywhere at once. Those waves cannot escape. As they rise toward the surface, the material above them thins out rapidly, and the waves bend back downward instead of breaking free. They travel down through the interior, curve around, and return to the surface somewhere else. Then they bounce again. The Sun is a sealed acoustic chamber. Sound is trapped inside it, ringing endlessly, unable to get out. And like any resonant object, it does not vibrate randomly. Certain wavelengths reinforce themselves and become standing waves. Astronomers have identified millions of distinct modes ringing inside our star simultaneously, and the strongest of them has a period of about 5 minutes. You can see the effect. The entire surface of the Sun rises and falls in a slow, tangled rhythm, as all those overlapping notes push it gently up and down. This is enormously useful. Just as a doctor learns about a body by listening to it, solar physicists learn about the Sun's interior by watching how its surface trembles. The path of each wave depends on the density and temperature it passed through, so the pattern of oscillations reveals the internal structure of a star we can never cut open. We now do the same for other stars. Space telescopes have detected these tiny rhythmic brightenings in thousands of distant suns, and from them we measure their sizes, their ages, and how fast their cores are spinning. Every star in the night sky is ringing quietly. We read their interiors by the notes they hold. The journey continues outward to the giants. Jupiter is the loudest radio source in the solar system after the Sun. Its magnetic field is 20,000 times stronger than Earth's, and it whips charged particles around at enormous speed, generating radio emissions so powerful that amateur astronomers can detect them from a back garden with simple equipment. Its moon Io makes matters more dramatic. Io is volcanically furious, and it feeds about a ton of sulfur and oxygen into Jupiter's magnetic field every second. That material becomes a glowing torus of plasma, and as Io plows through it, an electrical current of millions of amperes flows along the field lines connecting the moon to the planet. The radio bursts that result rise and fall with Io's orbital position. Saturn produces something different and, to many ears, more beautiful. Its radio emissions arrive as long, sweeping, layered tones with a slow rise and fall, recorded by the Cassini spacecraft across 13 years in orbit. And at the very end of that mission, Cassini did something remarkable. It threaded the narrow gap between Saturn and its rings, and its instruments listened for the impacts of dust particles. Engineers expected a roar. What they got was almost nothing. the gap was far emptier than anyone predicted. A strange, quiet corridor between a planet and its rings, discovered by a spacecraft that was about to be destroyed. And yet, there's more to this story, because one of the smallest objects we have ever visited turned out to be the most surprising. In 2014, a spacecraft arrived at a comet after 10 years of travel. The comet is a dark, dusty, double-lobed lump of ice, roughly 4 kilometers across, an insignificant object by the standards of everything else in this story. As the spacecraft settled into orbit, its magnetic sensors picked up something nobody had predicted. The comet was producing a steady, rhythmic oscillation in the magnetic field around it. The frequency was far too low for any ear. It sat at about 40 to 50 cycles per 1,000 seconds, which is roughly 10,000 times slower than the lowest note a human can perceive. Researchers raised the pitch by that factor to bring it into hearing range. What emerged was eerie and strangely musical. A clicking, warbling, insistent pattern, unlike anything from a planet or a star. The press immediately called it the Singing Comet, and for once, the nickname was earned. The cause appears to be the comet itself shedding water. As ice sublimates and the escaping molecules are ionized by sunlight, they interact with the solar wind streaming past. That interaction becomes unstable and begins to oscillate, and the oscillation propagates through the plasma surrounding the nucleus. A 4-kilometer lump of dirty ice drifting through the dark, generating a rhythm in the space around it for as long as sunlight keeps touching its surface. The universe puts sound in places you would never think to look for it. But what happens when we leave the solar system entirely? In 2012, after 35 years of travel, Voyager 1 crossed the boundary where the Sun's influence ends and true interstellar space begins. We knew it happened because of sound, or rather, because of the plasma waves that stand in for it. Voyager carries an instrument that measures oscillations in the surrounding plasma, and plasma has a natural ringing frequency that depends directly on its density. Thicker plasma rings at a higher pitch. Thinner plasma rings lower. When a shock wave from a solar outburst rolls past the spacecraft, it strikes the surrounding plasma and sets it ringing, the way striking a glass sets it humming at its own natural note. Voyager listens to that note, and from the pitch alone, scientists can calculate the density of the material the spacecraft is currently flying through. In 2012, the pitch jumped upward. The plasma around Voyager had suddenly become about 40 times denser. That is exactly what you would expect at the boundary between the Sun's bubble and the interstellar medium beyond. We did not confirm that a spacecraft had left the solar system by looking. We confirmed it by listening to the pitch of the space around it rise. Voyager still sends back that faint, steady hum today, from more than 20 billion kilometers away. A thin, persistent tone, the sound of the gas between the stars. And yet, there's more to this story, because some objects out there keep perfect time. In 1967, a young astronomer named Jocelyn Bell Burnell was reviewing data from a radio telescope she had helped build, printed on long rolls of paper. She noticed a strange smudge that kept reappearing, and when she examined it closely, she found a pulse. Then another, then another. They arrived every 1.33 seconds, relentlessly regular, to a precision better than any clock then in existence. Nothing in nature was supposed to do that. The signal was so artificial in character that the team half-seriously labeled it LGM-1 for Little Green Men. They genuinely considered, for a short time, that they might have detected another civilization. Then a second one turned up, in a completely different part of the sky, at a different rate. Two independent civilizations broadcasting identical metronomes was not plausible. It had to be a natural object. It was a pulsar. The collapsed core of a dead star, city-sized, containing more mass than our sun, spinning at tremendous speed and sweeping a beam of radio energy around like a lighthouse. Every time the beam crossed Earth, we received a pulse. Some pulsars turn a few times a second. Others spin hundreds of times per second, producing a steady hum rather than a beat. And when the beam of a fast pulsar is converted to audio, the result is a pure, unwavering tone, the sound of a dead star turning. Now, let's go deeper into the oldest sound of all. We have been treating the vacuum as a permanent condition of the universe. It is not. The universe has not always been empty. In the first few 100,000 years after the Big Bang, everything that exists today was compressed into a space vastly smaller and denser than anything now. There were no stars and no atoms. There was only a hot, glowing fog of particles and radiation, packed so tightly that it behaved like a single fluid. And a fluid can carry sound. Gravity pulled matter towards slightly denser regions. As matter piled in, radiation pressure pushed back out. In, then out, then in again. The entire universe oscillated. These were real acoustic waves moving through a real medium, obeying the same physics as a sound wave in air. The early cosmos was not silent. It was ringing. Then, about 380,000 years in, the universe expanded and cooled enough for electrons to combine with nuclei into neutral atoms. The fog cleared. Light streamed freely for the first time, and the coupling between matter and radiation that had carried the sound was suddenly broken. The ringing stopped instantly, everywhere, at once. But the pattern did not disappear. It was frozen in place, captured in the distribution of matter, and in the faint temperature variations of that first escaping light. That light is still arriving today. We call it the cosmic microwave background. And when we map its tiny, hot, and cold patches across the sky, we are looking at a photograph of standing sound waves in the infant universe. But what happens when we measure that frozen sound? Something wonderful. It behaves exactly like a musical instrument. When you pluck a guitar string, you do not get one frequency. You get a fundamental note plus a series of overtones at specific mathematical intervals. That pattern of harmonics is what gives an instrument its character. The early universe did the same thing. waves of different sizes were caught at different phases when the ringing stopped, and the result is a series of preferred scales imprinted in the sky. When cosmologists plot the temperature variations of the cosmic microwave background by size, the graph shows a large first peak, then a smaller second peak, then a third. A fundamental and its overtones, the harmonic series of the universe, and the exact positions and heights of those peaks are enormously informative. They tell us the geometry of space, the ordinary matter content of the cosmos, the amount of dark matter, and the age of everything. A great deal of what we know about the universe came from measuring the shape of a sound that stopped playing 13.8 billion years ago. The wave itself is still detectable in a second way. Each oscillation traveled outward until the moment the ringing ceased, leaving a preferred separation between concentrated regions of matter. That distance has expanded along with the universe, and today it measures roughly 500 million light-years. Galaxies are very slightly more likely to be found at that separation from each other. The largest sound wave ever made, still faintly visible in the arrangement of galaxies. The journey continues to something that is not sound, but insists on behaving like it. In September of 2015, 2 detectors in the United States registered a signal lasting a fraction of a second. 2 black holes, each around 30 times the mass of our Sun, had spiraled together and merged more than 1 billion light-years away. The collision sent ripples through the fabric of space-time itself. Gravitational waves are not sound. They do not need a medium. They stretch and squeeze space as they pass, and the detectors that found them measured a change in length smaller than a fraction of the width of a proton. But the frequency of that signal fell squarely within human hearing. As the 2 black holes closed in, they orbited faster and faster, and the waves they produced climbed in pitch. The final moments produce a rising tone that sweeps upward and cuts off abruptly at the merger. Physicists call it the chirp. It lasts about 1/5 of a second, and it sounds a little like a drop of water falling into a bowl, played backward. It is the sound of 2 black holes becoming one, recorded by an instrument that measures the shape of space. Nothing traveled through anything, and yet, played aloud, it is unmistakably a note. And yet, there's more to this story, because we have also sent microphones to other worlds. The first sounds ever recorded on another planet came from an unlikely place. In 1982, a Soviet lander touched down on the surface of Venus, into an atmosphere 90 times denser than Earth's air and hot enough to melt lead. It survived barely 2 hours, but it carried a microphone, and it recorded the noise of wind moving across that crushing landscape. In 2005, a European probe descended by parachute through the thick orange haze of Titan, Saturn's largest moon, recording as it fell. Titan's atmosphere is cold and dense, and it carries sound beautifully. The probe listened to the wind for 2.5 hours on the way down, and then kept recording after it landed. And in February of 2021, a rover landed on Mars, carrying 2 microphones. For the first time, we heard the wind of Mars, the crunch of wheels on Martian soil, the whir of a small helicopter's blades, and the sharp snap of a laser striking rock. Mars turned out to be extraordinarily quiet. Its atmosphere is less than 1% as dense as ours, so sound fades quickly and travels only short distances before dissolving into nothing. A conversation there would be a whisper at 10 meters and gone at 50. Venus is the opposite extreme. Its atmosphere is so thick and heavy that sound carries far better than it does here, and it also travels considerably faster. That density would change a human voice profoundly. The heavy air resists the vocal cords, lowering the pitch dramatically, while the throat resonates in a way that thins the tone. Anyone speaking on the surface of Venus would sound like a deep, buzzing bass. 3 worlds, 3 atmospheres, 3 completely different acoustic characters, and all of them real sound, captured by real microphones, carried by real air. Now, let's go deeper into the strangest acoustic discovery of them all. When scientists analyzed the Martian recordings carefully, they found something nobody expected. On Mars, sound travels at 2 different speeds at the same time. On Earth, all frequencies move at essentially the same rate. A drum beat and a flute note arrive together, which is why an orchestra sounds coherent from the back of a hall. Mars is different because its air is almost entirely carbon dioxide at very low pressure. Under those conditions, carbon dioxide molecules absorb energy from passing sound waves and release it again slightly out of step. The effect depends on frequency. The result is that sounds above roughly 240 cycles per second travel about 10 meters per second faster than sounds below it. Imagine standing at a distance and listening to someone speak. The higher parts of their voice would reach you before the lower parts. Music played across an open Martian plain would arrive out of order, treble first, bass trailing behind, the separation growing with every meter of distance. No human ear has ever experienced this. It is a property of an entire planet's atmosphere, discovered because we finally put a microphone on the ground and paid attention to what it heard. The universe does not merely have sounds we have never listened to, astronaut. It has kinds of hearing we have never had. The journey continues, and now something odd happens. Space reaches down and makes a sound directly in your own back garden. For centuries, people watching bright meteors reported hearing them, a hiss or a faint crackle, arriving at the exact moment the fireball crossed the sky. Astronomers dismissed these accounts for a long time, and their reasoning was sound. A meteor burns up around 100 kilometers overhead. Any noise it made would take about 5 minutes to travel down through the atmosphere. Hearing it simultaneously with the flash is impossible. The witnesses were right anyway. A bright fireball generates a burst of very low-frequency electromagnetic energy as it tears through the upper atmosphere. That energy travels at the speed of light, so it arrives instantly. And when it reaches the ground, it can make nearby objects vibrate. Dry grass, leaves, wire fences, hair, the frames of eyeglasses. Those objects become tiny loudspeakers. The sound is not made in the sky at all. It is made a meter or two from your own ears, by ordinary things around you responding to a radio pulse from a rock disintegrating far overhead. Something similar seems to happen during strong auroral displays. Researchers in Finland recorded faint claps and crackles during intense aurora and traced their origin to a layer only about 70 meters above the ground, where charge accumulated in cold, still air appears to discharge. Which means that on rare nights in quiet places, the sky above your head genuinely makes a sound. Almost nobody has ever heard it because it requires darkness, stillness, and complete silence. But what happens when we turn sound into a tool? Nearly everything astronomers work with arrives as numbers: brightness over time, frequency against intensity. Traditionally, all of it is turned into images and graphs because sight is how most people process data quickly. But hearing is remarkably good at certain things that vision is poor at. The ear detects faint, periodic patterns buried in noise with astonishing sensitivity. It tracks several simultaneous streams at once. It notices small changes in rhythm and timbre that the eye slides right past on a chart. So astronomers began converting data into sound deliberately. The practice is called Sonification, and it is now used across the field, on black hole imagery, on nebulae, on the light curves of distant stars. The technique also opened astronomy to people who had been shut out of it. Researchers who are blind or have low vision have used sonification to analyze data independently, and in several cases have identified features in the data that sighted colleagues had missed entirely while looking at the same information as a picture. There is a quiet lesson in that. For 400 years, astronomy has been an almost entirely visual science, built on lenses and mirrors and photographic plates. It turns out that some of what the universe has to tell us was never best suited to the eye. We were only ever using one sense. There was another one available the whole time. The journey continues, one last time, to a sound moving away from us forever. In 1977, 2 spacecraft left Earth carrying identical gold-plated records. Each one holds greetings in 55 languages, music from many cultures and centuries, and a collection of the sounds of this planet. Thunder, rain, surf breaking on a shore, wind in trees, crickets and frogs at night, a heartbeat, footsteps, a mother speaking to her child, the song of a humpback whale. Both records are now beyond the edge of the solar system, moving outward at more than 50,000 kilometers per hour. They will not approach another star for tens of thousands of years. The odds that anyone will ever find them are essentially zero, and the people who made them knew that perfectly well. The record was never really a message to anyone else. It was a statement about what we thought was worth keeping. They are also, in a strange way, the quietest objects in this entire story. Every sound on those discs is sealed in a groove, in a vacuum, unable to make a single vibration in anything. They carry the noise of an entire living world in perfect, permanent silence. If one is ever recovered in some unimaginably distant era, the sounds of Earth will play again in a room we cannot picture, for an audience we cannot imagine. But what happens at the very end of all this listening? Sound requires a medium, and a medium requires matter gathered closely enough to push on itself, which means sound in this universe is not permanent. It is a temporary privilege, available only while things are still crowded together, and the universe is steadily becoming less crowded. Space is expanding, and that expansion is accelerating. Gas clouds are being consumed by star formation faster than they are replenished. Galaxies are drifting beyond each other's reach. Every process we have followed tonight depends on material being close enough to matter nearby, and across enormously long timescales, that condition is quietly disappearing. Eventually, the last stars will burn out. The gas between them will thin past the point where any wave can propagate. The hot clouds and galaxy clusters, which today carry the deepest note in the cosmos, will cool and disperse until nothing can ring through them. At that point, the silence becomes complete and permanent. Not silence in the sense of nothing being heard, but silence in the sense that a pressure wave could no longer physically exist anywhere in the universe. Every sound in this story, then, belongs to a particular era. The ringing of the early cosmos has already ended. The note in the Perseus cluster will fade. The sun's trapped chorus will stop when the sun does. Even the wind on Mars will eventually still. We happen to be alive in the loud chapter. It will not always be this way, and that makes it worth listening to now. Take a quiet moment to reflect on what this means, astronaut. We began tonight with a simple idea. Space is silent, and it is almost everywhere, almost always. But we found the exceptions. A black hole holding one note for billions of years. A planet singing at dawn in a register we cannot hear. A dead star keeping better time than any clock. An entire universe that once rang like a bell and left the echo written across the sky. Wind on 3 other worlds, recorded by machines we built and sent away. None of it was made for us. Not one of these sounds was meant to be heard. They were simply happening, patiently, for billions of years before anyone existed who could wonder about them. And perhaps that is the most comforting part. The universe is not performing. It is not trying to be noticed. It simply carries on, vibrating in registers too deep and too slow and too faint for us. And every so often we build something clever enough to catch a little of it. Silence, it turns out, is mostly a statement about the listener. The cosmos was never quiet. We were just not equipped to hear it yet. We drift homeward now, back through the empty places where no sound can live, past the humming plasma, past the singing magnetic field, down toward the thick, warm, noisy air of home. Here sound works everywhere. Every breath you take moves it. Every small sound in the room around you right now is a thing most of the universe cannot do. Listen for a moment. Whatever you can hear tonight, however ordinary, a clock, the wind outside, your own breathing, is something rare and precious in this cosmos. Now let it fade. Let it grow soft and distant, like a tone dissolving into thin air. There is nothing left to listen for. Mission complete, astronaut. The stars will wait for you. Good night.